Hey guys, Mr. Champlin here. Today we're going to be talking about gravity and Newton's universal law of gravitation. So what is Newton's universal law of gravitation? So as the name suggests, the word universal, what does that mean? So we talk about a universal suffrage and social studies and that sort of thing. So here it has a little bit of a different meaning. Universal means that no matter where we go in the universe, this should hold true. So this is one of Newton's most famous, contributions to science. So what was he saying? Well, he was saying that there is a force of gravity between any pair of objects anywhere in the universe. So if we have two objects here, mass 1 and mass 2, they are exerting this gravitational force on one another. They are pulling, they are attracting one another. They are pulling towards each other. It doesn't matter if we're talking about two planets, if we're talking about the sun and a planet, if we're talking about the Earth and its moon, or we're talking about two specks of dust. It doesn't matter. Anything with mass is going to exert a gravitational force on everything else with mass. So here's the formula that he uses right here. The force of gravity is equal to G times M1 times M2, and we divide by R squared. Now I want to point out that this R squared, R stands for radius, but don't be confused. The radius is just simply the distance between the center of one object and the center of the other object. So it helps to just think of it as the distance. M1 and M2 obviously are the masses, and we measure mass in kilograms. And G, as we'll talk about in just a moment, is an important value that we're going to need to use. So in words, what is his law saying? It's saying that the force is proportional to the mass and inversely proportional to the square of the distance. So what do we mean by that? So first of all, let's talk about this G. So G is the universal gravitation constant. So in other words, this is a number that we have to plug in to sort of make things, come out to the right thing. So we've seen this before earlier this year, way early in the year, when we talked about the force that's exerted, the electrical force that's exerted between two charges. So this formula is very, very similar. So the universal constant G is 6.67 times 10 to the negative 11. You don't really have to worry about the units because they end up all canceling out. But 6.67 times 10 to the negative 11. So it's a very, very, very tiny number. And this is simply because gravity is not a strong force. Gravity can act over a long distance, but it's not a particularly strong force. Okay, now again, let's go back to this idea of universal gravitation. What is this formula actually telling us? What is it saying in words? Well, if we have two masses here, right? What it's telling us is that if we increase the distance between the two masses, then the gravity will go down. And of course, the opposite is also true. If we decrease the distance or bring them closer, then the force of gravity will then go up. Okay, that makes sense. So the distance is inversely proportional to the force of gravity. Or in other words, when one goes up, the other goes down, and vice versa. But the mass is proportional to the gravity, which is to say, if the mass were to go up, the force of gravity would also go up. If the mass were to go down, then the force of gravity would also go down. All right, so one thing I should mention is that gravity, when things are in space, they are going to form a spherical shape, right? So this is why all planets and stars and everything have a spherical shape. The Earth actually started out as just a cloud of dust, and those little bits of dust exerted a gravitational force on all the other little bits of dust and came together to form the Earth. So in space, typically, things will form a spherical shape. Of course, there's always exceptions, to that, but anything above a certain size or below a certain size is going to definitely form a spherical shape. Now, I do want to talk about orbits. Why do things orbit other things? For example, why does the moon orbit the Earth? Why does the Earth orbit the sun? Why does the International Space Station, why does it orbit the Earth? So we need to go back and talk about movement in 2 dimensions. We will also be talking about forces in 2 dimensions a little bit later, but for now, just think about something that's moving in 2 dimensions. So, for example, Newton did a thought experiment where he said, if I have a cannon on top of a very, very tall mountain and I fire that cannonball, what's going to happen? Well, the cannonball has a forward motion because of the explosion of the gunpowder inside the cannon, but also it's going to have a downward motion because the gravity of the Earth is going to be pulling it down. So now Newton never actually did this. It wasn't really possible, but it was a thought experiment. It's something he imagined, and actually it really works well to describe what's happening, right? So if this cannonball gets fired very fast, it's going to just fire and it's just going to go away from the Earth. However, if you fire the cannon too slow, it's simply going to fall to the Earth. All right, but if you balance those 2 forces just right, the speed of that cannonball being fired with the gravity of the Earth, you can actually cause the cannonball to orbit the Earth. So in other words, it's always falling towards the Earth, but it never hits the Earth because of this forward motion that it has. So this is how we can explain why the International Space Station, for example, is able to orbit the Earth, or satellites, right? Lots of satellites that orbit the Earth and allow you to get satellite TV or allow you to use, GPS. So things that are orbiting the Earth. So let's talk about that for a second. So if you're in the International Space Station, it's orbiting the Earth, what do you notice? Well, it appears as if there's no gravity, right? People are floating around, and you've seen this in movies. But what if I told you there actually was gravity in the International Space Station? The International Space Station is actually not that far from the Earth, right? It's just out of the Earth's atmosphere, and it's just in the very edge of space. Okay? Now, how is that possible? How can it be so close to the Earth and there be gravity, but yet when you look at them, they're floating around as if they're weightless? Well, we can explain that because, again, of this sort of falling concept, right? That this International Space Station is always falling towards the Earth, but it doesn't hit the Earth, right? So it keeps orbiting, it keeps going around and around. Now imagine if you were in an elevator, and imagine if that elevator started to free fall and it kept falling. And let's just say it could fall forever. If we looked inside that elevator, and if you were staying on a scale, you would be weightless. You would have no weight at all. All right? So this is actually what's happening inside the International Space Station. Because it's falling, the people inside appear to be weightless, even though there is plenty of gravity from the Earth that is pulling on them. All right. So let's take a look at an example of the law of universal gravitation. So here we have a problem. It's asking us, what is the force of gravity on two planets that pull on each other with a mass of 1.23 times 10 to the 26th kilograms and 5.21 times 10 to the 22nd kilograms, and they're 230 million kilometers apart. So first of all, let's take a look at r, or the radius. Now they give us the distance, or the radius, in millions of kilometers. Now we have to measure the distance, or the radius, in meters. So you'll notice that it says 230 times 10 to the 6th, so that's 230 million meters. But then remember, we're going from kilometers to meters, so that's an extra 10 to the third power. So really, I don't know why they wrote it this way, but they should have written it 230 times 10 to the 9th power. Here, of course, we have our G, our universal gravitational constant. Excuse me. Of course, here's the mass of our two planets. There's the one, there's the other. Now again, these problems are not difficult. The only thing, the formula is fairly simple. The only thing that makes this difficult is that you're dealing with very big numbers and very small numbers. So you got to make sure that you know how to use your calculator properly and that you know how to put in the scientific notation into your calculator. So if you have any questions or problems with that, just let me know and we'll try to get it sorted out. So once you sort of plug everything in, of course, you would multiply all this together. You would divide by this, and here is your answer. Notice that our answer is measured in newtons, right? And that's because newtons is a measure of force. Also notice that it's 8.08 times 10 to the 15th newtons. So that's a lot of newtons. But again, we're talking about the gravitational force between two planets, right? If we were talking about the gravitational force of a person on another person, your masses would not be that great, right? So therefore, the force of gravity would be probably measured in millionths of newtons, right? So a very tiny, tiny amount of gravity, which is why people don't normally are physically attracted. In other words, they don't pull towards each other. Although I'm sure if you're in a bar, you can make all kinds of great universal gravitation jokes. All right, so hope that was helpful. If you have any questions, of course, don't hesitate to contact me via email or through Teams, and we'll try to get things straightened out. I have some problems, some practice problems for you. Not too many because, of course, these can be quite, quite cumbersome to solve. So just a few problems to kind of get the physics, juices flowing. And again, if you have any problems, don't hesitate to contact me.